Okay, class, when we discussed the heat flux in class, we did not get to the last problem, which discusses, sort of looks at the heat required to change the temperature of the water. So we looked a lot at heat flux coming into the ocean. What are the repercussions? Well, it can heat or cool the ocean. And so we have to think about an energy balance to look at how much. So let's consider a cube of water. We'll give this cube some dimensions. So let's say its depth is h and its horizontal extents are going to be, I don't know, we'll call it L and W. So we have a volume for this box, L times W times H, where L and W are equal to the surface area of the box, the free surface area. So the heat penetrates to the top here, and through this top surfaces of area, L times H, or S. So that's our total volume. The water in the box has a density, constant density rho. So the first question we have to ask is, okay, given the volume of the box, given the density of the box, how much energy does it take to raise or lower the temperature of that box by a certain amount? So let's say by a delta T. So we want to figure out the delta E required to change the temperature in the box by a delta T. And so the answer to that is delta E is equal to the mass of fluid in the box, simply rho times V, times a thermodynamic variable, which is the specific heat at constant pressure, which is a measure of how much energy you can store in a kilogram, or how much energy is required to raise a kilogram of this material, water, by 1 Kelvin. That's your CP. And rho V times Cp. So this is our fundamental energy balance. And so let's make sure that the units are going to work out here. So this is equal to kilogram per meters cubed. We should start with joules on the left, fundamental unit of energy in SI, times meter cubed, that's our volume, times, I forgot something here, let's backtrack. Change in energy obviously depends on the required change in temperature. So times joules per kilogram Kelvin. That's the units of the specific heat. Times delta T. Oops, I wasn't writing that. I need to write the units for delta T. Kelvin. So let's cross our units. Kilograms are gone, kelvins are gone, so we get joules. Joules equals joules, the units check out. What about what's going on? Well, we can see here delta E goes up under what conditions? Well, if the temperature change required goes up, if the volume goes up, any of the dimensions, if the density goes up, that means more mass for a given volume, or if the specific heat goes up, that means more energy required for a given mass to raise 1 degree Kelvin. For water, Cp is approximately 4,000. That's okay for rough calculations. It is not a fixed property either. Don't use that for air. Air is much smaller. Air can't store nearly the amount of heat in a given mass. So use Cp is 4,000 unless you are trying to go for an accurate equation or you're told otherwise. So this is the energy required, change in energy required. Then we think, okay, where's the energy coming from? It's coming from the heat flux, again, to the top of the box, to this surface area S, we have a certain Q. And so Q is of units, watts per meter, meter squared. That's the amount of energy per unit time that's passing through every square meter of the surface. So if we want to get a total energy out of this, so this would be a delta E input into the system. This is going to be our heat flux. Our heat flux, it's supposed to be a Q, times the amount of surface area. So we have more energy going in if we have a greater surface area for a given heat flux. So heat flux is per meter squared. So the heat flux going into Clark's Cove that we'll do later, it depends on the surface area of the cove. Times surface area times time. If that heat flux is acting for a longer time, longer delta T, then we have a greater amount of energy that's going in the system. So now we can set these two to be the same. So we have Q dot S dot delta T is equal to rho V Cp delta capital T, change in temperature. So little t is time, big T is temperature. This is the basic relation. between these two things. Again, we're assuming that the water is perfectly mixed in the box. We have a single row and that the temperature is, that the entire temperature of the water is constant. So then we could say, okay, we can answer some questions. One is, for example, a time scale. What's the time scale required to raise the water a certain temperature, given a certain heat flux, given the amount of water we have? So we're going to write that this way, and we'll see we get some simplification. In fact, I'm going to back up here and apply the simplification right here. So let's expand this out a little bit. I have Q times S times delta T equals rho V Cp delta capital T. So it kind of appears that S is explicitly going to arrive in some of these formulas. But if I expand out V as equal to S times H, as I did at the top, surface area times the depth, then I find out I have Q S delta T is equal to rho S H Cp delta T. So I can kill, or I can wipe out one of my S's, and I'm left with an expression that only has a single geometric dimension, which is the depth. So this is important. This means is that as my surface area grows, if my depth is fixed, I'm getting more volume. So I need more energy to change the temperature, but I'm getting more surface area at the same rate. So I have more energy going in. So those two things balance out exactly. If I have a fixed surface area and I start messing with the depth, I'm changing the volume, but I'm not changing the surface area at which, I'm not changing the surface area, so I'm not changing the amount of heat that's getting absorbed. And so we can see that H is important, and if we look at the time scale here, to change the water by a certain temperature delta T, I have little delta T, equals rho H Cp delta T divided by Q. And so we can see here, look in these variables, that if the density goes up, or Cp goes up, basically my ability to store heat in a given volume, or the energy required to change the temperature by 1 degree Kelvin, is going to increase because I have more mass in a given volume. If my depth goes up, my time required goes up. If my temperature change that I need to change it by goes up, my time required goes up. If my heat flux goes up, denominator down here, I have my time scale goes down. I can also think about a rate of change. What's the estimate for the rate of change of temperature? Delta T, big capital T or a little t, so change in temperature over change in time is going to be equal to Q rho HCP. So we invert this expression, so higher heat flux is faster the rate of change in temperature, and these other variables will cause that to increase. If I consider something like Clark's Cove, this is Clark's Cove, think of a little pond, has a depth H, it has a volume of 15 million meters cubed, it has a surface area of, I think it's 3 million square meters, and I have an average depth is equal to V over S. It's going to be 5 meters. It's the average depth of Clark's Cove. And so I might ask the question, what heat flux is required to raise the temperature of Clark's Cove by 1 degree Kelvin in 1 day? So I have to give it a time scale. I have to say it has to be raised in a day. And so if I solve up here, or let's even back up a little bit further, I have this expression here, and I'm going to solve this for Q. So I say here Q required, and I want to know what Q is, to raise it a certain delta T times rho HCP divided by little delta T, by the time difference. So I can see here is if I want to raise the temperature to a larger number, my delta T goes up, I'm going to need more Q. If I have a higher specific heat, I'm going to need more Q. If the density is higher, I have more mass in this volume, I'm going to need more Q. If the depth is greater, I'm going to need more Q, more heat flux. However, if I allow a longer time scale, let's say, okay, I'd like to raise the heat over a year, I don't need a strong Q to do a given delta T. Or if I say I want to raise the heat by delta T in 1 second, I can see that I'm going to need a very big heat flux in order to do that. We could plug these numbers in. Essentially is 1 Kelvin times 1,025 kilogram per meter cubed times 5 meters times 4,000 joules kilogram Kelvin divided by 86,400 seconds. It's 1 day. And let me just do this out with Python. Give me a second here. 1025, 4,000 times 5 times 1, 86,400. And I get 237 watts per meter squared. With a heat flux of 237 watts per meter squared, I can increase the water temperature in Clark's Cove, given its volume and properties, by 1 degree Kelvin in 24 hours. And so in class we talked about at times the heat flux can exceed this, particularly during the middle of the day when you have a strong shortwave signal. You can get a much bigger value than this, but averaged over the course of a day, you have positive, sometimes positive and negative, or positive and strongly negative, and you can have terms that to get an average over the day. And so again, this is averaged over a 24-hour period. We end up with 237 watts per meter squared. So that's a number that we calculated for this case. We can clearly see if Clark's Cove were deeper, that this number would have to go up because the volume's going up, but the amount of heat captured to the surface didn't change. And so that's something to consider. Clark's Cove is actually fairly shallow, 5 meters. Okay, that's all I wanted to say about that problem.